thanks for the introduction, and thanks the organizers for putting together this workshop and the invitation to be here. So today, so the general theme of this workshop is to get rid of gate, thinking about analog. So I'm going to try to motivate the opposite story. So I wanted to introduce gates to a really, really hybrid, really analog system, and then see how we can actually, carefully analyze the computational power of these analog systems by actually introducing the gate models. Maybe in the future we'll remove the gate, but at least we see some interesting results here. So this is a giant collaboration across multiple institutions. So we have a long author list. I'm gonna not go through them, but Shraddha Singh and Kevin Smith are also the main contributors here. And also we have Alex Schuchert also in the audience today. So let me say a few words about my group. So we are a theory group, generally interested in quantum engineering and simulation theory. And so one of the areas we're very interested in is to develop quantum algorithms for quantum chemistry and material simulations. So the second sort of direction is something that I'm going to focus on today, is to really think about how we leverage this hybrid digital and analog quantum systems for interesting applications or even fundamental control protocols. And so the third is broadly interested in quantum engineering. For example, metrology, sensing, how the signal processing, how the traditional concept in ECE, electrical computer engineering, can be developed further given development on quantum. And so I want to start the story by just showing this really simple. In classical computing, we have digital and analog components, and those are built in our devices right now every day. So on the quantum domain, we also have digital qubits and also analog systems. For example, oscillators. Right? So these are well known in quantum optics, and also even existing molecules and materials or trapped cavities. And so the physics of these qubits and oscillators are well known. For example, if we wanted to analyze oscillators, we're going to write down their Hamiltonian and then quantize those. And then we typically see an evenly spaced energy spectrum, and then we can define their energy eigenstates. And then we can go ahead and try to write down operators how to control these oscillators. And then we usually draw a lot of analogy by analyzing this, comparing to classical oscillators, because that's something we kind of have lots of intuition. So we have the coherent states, and then we can think about how coherent states moves and superposition of coherent states in phase space. So that gives us a lot of intuition. And then we can quantize this and introducing momentum and position. That's, again, classical mechanics concept. We kind of also have a whole framework of phase-space quantum mechanics to deal with all of this stuff. So the algebra between oscillators and qubits, as you see here, is really different. For example, qubits, we care about Pauli's generators. And oscillators, we have position and momentum. And then their commutation relationship are really different. So that gives us a question. Even if we know the physics of oscillators, we might not actually know their computational power that well. And so the talk today, I'm going to try to, by introducing gate models in these hybrid qubit oscillator systems, and then that will help us to analyze, some the computational power of the system, and I will show you some applications later on. So we have some, belief that oscillators is powerful. For example, in the past few years, there has been lots of quantum control protocols by hybridizing qubits to oscillators, and then using oscillators, for example, as qubits, as hardware efficient memories. There is also, bosonic error correcting code developed on this based on oscillators that was among the first to demonstrate a memory break-even on real hardware, given a realistic noise. And third, if we think about applications, oscillators, lots of degrees of freedom existing in quantum chemistry or materials or even high energy physics. So if we can really leverage oscillators, we might be able to simulate those systems in a better fashion. Right? So there are challenges. I will just quickly go through some of the challenges. First of all, we need universal control of oscillators. And we know qubit super well. So it might be good that we actually wanted to hybridize, right, these two components. And what we really want to do to analyze the computational algorithmic level is to go beyond the physical layer. And then we wanted to think about how actually to program them, how to actually reason about their computational power, and how to actually perform resource estimation for different applications. So this gives us, the central thesis of my talk is really that we need to abstract the machine model that just as theoretical computer scientists analyze classical computers or qubit-based quantum computers. And the second, we need universal instruction set that can actually allow us to say, okay, what is possible, what is not possible. Among the possible applications choices, how much resource do we need? And so this is the outline. So I'm going to start by delve a little bit into what are instruction set architectures and abstract machine models for this kind of hybrid processors. And then I will see how we can actually now go from there, develop algorithms to actually program or control this kind of hybrid analog digital systems. And I will show some applications later on and then conclude with some open questions. So for some of you who might not know, this is really just the computer science jargon, right? So abstract machine models. We know lots of physical systems can be built and be used for computation. So we wanted to abstract away the physical details and then just to think about a mathematical model that's simple to analyze. For example, for classical computers, Turing machine is one of the typical abstract machine models where you have a tape and then each cell of the tape writes some alphabet, a program that tells a finite state machine how to move between its internal states. And then you have a read and write head that read whatever stuff on the tape and then decide what to move or write on that spot. And then you start from somewhere. When the whole process stops, that's when your computation stops. And then you can go ahead and read whatever was written on the tape, and it tells you the results of the computation. Right? So some of the more modern instruction set. So this is one of the first digital classical computers in 1949. And then you see there are more interesting instructions. For example, we're more familiar like additions and logical operations and all that, right? So what about for quantum computers? Of course, for qubit-based quantum computers, this has been a long history in the past few years and also decades on developing all of this for qubit-based quantum computers. For example, this is a paper by Microsoft that was trying to say, okay, on qubit, we can sort of think about similar things, and we can say, start from high-level programming languages and applications all the way to low-level device controls, and then instruction set lies in the middle that helps us to bridge the high-level applications and low-level implementations. And there is also similar works by IBM and also Google. And it turns out that this instruction set architecture will be the key to actually perform rigorous resource estimation and allows you to determine for what applications, what tasks, the computation, the quantum or classical, will be useful and have advantages. Right? But this kind of stuff is unknown for hybrid digital analog systems. So let's dwell on this problem a little bit and think why it is really sort of challenging or difficult. Right? So we need an architecture physical layer. And then also to do computation, we sort of need error correction. And then we need a full stack approach to go from encoding to realizing logical operations and then on these hybrid systems. And then to compile that into high-level algorithms, and then also to address a target applications. And universal gate set is what I mentioned about instruction set. So the compilation method that actually can help you decompose the algorithm into the gate set. So let me start by describing some of the physical layer. So we see here, these are three of the major quantum computing architectures. And actually, oscillators are built in all around, which we might just not be aware of them. For example, one of the leading architecture in trapped ion, right? Normally, we just say, okay, we do a two-qubit gate. But actually, under the hood, the 2-qubit entangling gate has to be mediated by the oscillator, which is the vibrational mode or motional mode of the eye. And now if you see the superconducting platform, usually you could have transmon qubit coupled to a microwave resonator. And then it's sort of similar architecture, but the connectivities and the available gate set might be different. And in neutral atom, right now we mostly talk about qubit-to-qubit interactions. But if you think about the atom got trapped into the optical tweezers, then the atom in principle could move, although it might just be really thermal and not really quantized motion. But maybe better control techniques can enable that in the future. So given this hybrid oscillator-qubit hardware, so I wanted to sort of pivot toward 3 different kind of abstract machine models. So one of them is what we call qubit-centric. For example, in a superconducting platform, what we have is that we have an array of high-fidelity oscillator that only have a nearest neighbor coupling, mediated by super high-fidelity swap gate. And then each cavity got coupled to, let's say, a qubit or transmon, which has low lifetime, smaller lifetime. And now if you actually use this stuff for computation, use qubits for computation, then the oscillators can serve as a really high-fidelity bus that produce long range entanglement between the qubits. And now if, on the other end, you would want to use this for oscillator-centric computation, you would think that, okay, now oscillator really encodes the quantum information you care. And each qubit can serve as a quantum control handle that allows you to actually manipulate or control the oscillator in some arbitrary fashion. I will show you how to actually do this in an arbitrary fashion later on. And then you can also think about, for some applications, maybe qubits and oscillator are both useful and interesting. Then you can kind of just say, okay, you encode quantum information in both, and then see how the computation gets you there. And just I wanted to show this really computer sciencey stacks. Everybody wanted to talk about that. So I wanted to highlight that if you have a hybrid oscillator, something changed. For example, here on the algorithmic level, you could think about some continuous variable CV algorithms that could be possible on this hardware. And I'll give you examples of what are some of these CV algorithms or even hybrid algorithms. And programming languages, you might think about redesign whatever programming languages one developed to actually program and control these analog devices. And here the compiler and the instruction set, so there is a layer on quantum error correction that's hidden here. So for example, if you actually just use this physical layer devices for logical qubit computation, right? So you actually kind of need to use all the bosonic error correcting code. And then so there has to be the transpilation compilation from logical qubit operation to the physical operations on the oscillators. But if you just use the hardware efficiency of oscillators, you might actually just not need oscillators. But of course, the coherence time will be limited to some extent. And so I wanted to delve a bit into the quantum control and instructions of these hybrid systems. So for qubits, we know that we just have to generate all the Pauli generators, which is easy. And then for oscillator-only control, so we know from previous results that all we need is basically a generator that is a polynomial or analytical function, but oftentimes approximated as a polynomial of the quadrature operators. And Gaussian operations will not give you that universality. You kind of need some nonlinear, non-Gaussian operations. So one of the typical used control is the cubic phase gain, and then just the x to the third power. But if you think about this, how do we then think about universal control of a qubit and oscillator? So here we just need a polynomial of x and p. And so for hybrid qubit, a single qubit and single oscillator, you actually need 4 independent polynomials of the quadrature operator of the oscillator. And so it's kind of really simple because qubit just have the 3 polys and identity. And use the tensor product, the 2 of them. So this gives you 3 for the polys. This gives you 1 polynomial for the oscillators. And then the goal of really doing or thinking about computational control are to see how you can actually approximate these polynomials, the 4 of them, on just a single qubit oscillator. Or if you have even more qubits oscillator, it's going to just have more functions. So everything will become, again, a function approximation on the quadrature operators of the oscillators. And so it turns out that there are 2 very simple universal gate sets to think about how this can be, this computation can be performed. So one of them we call phase space instruction set. The other we call Fock space instruction set. So what does the phase space instruction set composed of? It has some entangling gate between qubit and oscillator, which we call conditional displacement. And these are well known for some communities. And then we also need a single qubit rotations, arbitrary rotations. And then also the beam splitters between the oscillators. And the intuition is really that if you think a word about what this conditional displacement does, if you start from the vacuum state of your oscillator, coupled to a qubits, right? And then depending on what the qubit is on the 0 or 1 state of that poly Z, it kind of displays the oscillator towards the left or towards the right, or depending on whatever complex number alpha is, toward 2 different opposite directions. And each one of the displaced vacuum now got entangled with the eigenstate of that poly of your qubits. And now suppose now you do a qubit rotation. You redo a different conditional displacement. The original splitted 2 coherent states now will again split into another 2. And so you can kind of continue this reasoning of saying that the number of coherent state blobs in your phase space will grow exponentially as the circuit depth increase in this kind of instruction set. And that really just gives you universal control. And of course, the phase space blobs are not orthogonal. To really prove that it's universal control, it has some connections to frame theory and wavelets, which I will not go into detail. And so the second kind of Fock space instruction set is independently universal. So the key gate here is really just a qubit Fock state control, oscillator Fock state controlled arbitrary qubit rotation. You can kind of think this gate is really powerful because it does a qubit rotation differently, conditioned on each Fock level of your oscillator. And on hardware, it's kind of easy to realize for superconducting microwave cavity systems. And of course, beyond that gate, we need unconditional displacement, which is the drive on the oscillator, and also beam splitters to entangle them. And so either one of them will basically give you a universal control on arbitrary n qubits and m oscillators. And then the oscillator part is really, think in terms of in the phase space picture how things got transformed and computed. And so with that basic gate, right? So this is like the Clifford, non-Clifford gates we are familiar for qubits. And now how do we develop algorithms? So it turns out that if you introduce gate models, lots of the algorithms on DV can be naively generalized to the hybrid CV-DV scenario. And then you can use the results there to analyze what the computational power of this hybrid devices are. So there are a whole bunch of new results in our paper, but I will just focus more on this extension of quantum signal processing from qubits to hybrid systems and show some applications later on. But also I wanted to highlight some results we have on analytical techniques to compile long-range multi-qubit gates and also multi-oscillator gates. So this gate compilation, I think I'm going to try to skip. And so you can read more details in the paper. But one of the key techniques for getting these multi-qubit gates shares some similarities from the Moment-Sorensen gate in trapped ion that people use to compile entangling qubit gates. So what you usually do is that the key is that displacement in oscillator phase space does not commute. So if you start your oscillator in one place, whatever trajectories you go, and then you return to the original position, there is a phase that's got kicked back. Then that phase kickback can be picked up by the oscillator, by the qubits computational basis. And you can just control the area of that enclosed loop in phase space for the oscillator to compile any multi-qubit or two-qubit entangling gates. And so you can also use that to analyze the similar results that, okay, this kind of compilation really have high fidelity, doesn't depend on the thermal excitations or dephasing errors on the oscillators in similar fashion as Moment-Sorensen gate was analyzed. How much time do I have?
About 7 minutes.
7 minutes, okay. So I'm gonna try to highlight some of the results. So I think the difficult part of really thinking about algorithms is to control the single oscillator. Because if we think about multiple oscillators which have beam splitters, we can entangle different oscillators. But how do we reason about just to control single oscillators? And so I wanted to show you quickly some powerful algorithms that was developed in the past few years, decades on qubits that was really general, that pretty much unifies lots of the known quantum algorithms. That's called quantum signal processing. And of course, there are early works on product formula that was generalized to hybrid systems that shows, okay, you can actually just compile bosonic devices also in a product formula sense. So I want to see, okay, give you just a taste of how this works. Quantum signal processing on qubits. The way it works is really simple. Suppose you are given a block-encoded amplitude, for example, in this case A, and this is really the single qubit version, not high-dimensional version. And you can view this as a sigma x rotation. Now A is fixed. And now you can also have access to orthogonal rotation, for example, sigma z rotation here, where the rotation angle is tunable. And then from the orthogonal rotations, you kind of know that, of course, this too will give you pretty much a lot of computational power, because x and z does not commute, it can generate lots of things. But suppose you fix this x rotation, right? You only tune the z rotation. So if you chain lots of this together in an alternate fashion, xz, 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 you repeat d times, you can kind of show that the resulting polynomial, the resulting unitary, are really just a polynomial transformation on the block-encoded constant scalar amplitude A that you have. And so this polynomial, of course, will have lots of constraints and all that, actually mild constraints. And there are newer works that remove these constraints by even generalizing this. Right, so if you can design your polynomial to different shapes and to different degrees, you can actually approximate any analytical function on this amplitude. Right, so that really gives you lots of computational power. And then that's how, the essence of how this algorithm really achieves, reproduce lots of known quantum algorithms. And so this polynomial picture can, of course, be related back to the signal processing filter design idea in the ECE community. And that's actually how this algorithm comes from by Lo and Tron a few years back. So in signal processing, we know lots of interesting tasks can be just reformulated as a filter design. And of course, now we have a quantum circuit that does that transformation, that filter design on quantum amplitudes. Now, if you think about this, how this works, right? So the key is that you have some amplitude that's block encoded. And in the oscillator fashion, all we care about is just the quadrature operators. And if I write down a simple entangling gates between the qubit and oscillator, what I can see is that the oscillator quadrature operator raised to some power is also just the one block of my 2x2 matrix. And therefore, that just gives me a natural block encoding of the oscillator quadrature operator up to a constant, k, kappa or k, there. And then with that, I can then chain together that simple entangling gate with a unentangled qubit rotation. And this qubit rotation phase angle I can still change and adjust. So that will give me a polynomial transformation on the oscillator quadrature operators. And because I mentioned that anything can be represented as just the polynomials on the oscillator quadrature operators, and therefore you can kind of increase the degrees and then change the phase angles to control that polynomial. So this will give you universal control on the oscillators. And you can kind of also bound this error depending on what the constant k and lambda there is. So that basically sets some truncations on your phase space. So all of this framework basically give you a bounded error that you can rigorously analyze quantum controls algorithms on these hybrid analog digital systems. And so there is the open question that we have not resolved is that in the oscillator you have x and p, which does not commute. But the original quantum signal processing works for a single variable. And how do you actually, approximate a non-commutative, non-abelian two-variable polynomials? And so in this setting, so that seems to be the simplest non-abelian multivariate polynomial approximation that we can find that has natural connections to real sort of experiment and physics. But even that is a difficult problem. And you can also trivially generalize the linear combination of unitaries to the hybrid case, where let's say you can do the linear combination probability distribution on either the qubit or oscillators. You can kind of show if you actually do some state preparation, and then you do an entangling gate between the oscillator and the qubits. In the end, it's possible to realize a continuous probability distribution of your qubit rotations. And that's really in a continuous picture that you can initialize and manipulate the oscillator in some sort of similar fashion as you thought about qubits. And so I wanted to maybe speed up a little bit and just glance through these examples because I run out of time, right? From this universal control, what we show that we can actually develop a mixed analog digital quantum signal processing framework that will allow us to perform quantum digital analog conversion, just as the similar case in classical signal processing between analog signals and quantum signals. So you can see that preprint for more details. And then what we showed is also that if you can now convert digital signals to analog systems, some tasks might be really simple for analog systems. For example, the Fourier transform are just the free evolution of the oscillators. So what we show is that you can kind of just encode the qubit data into oscillators and then wait a little bit. So that will give you the Fourier transform of the n-qubit quantum data in a really simple fashion. But of course, there are detailed error bounds we work out that you can see. And also, we showed an example of how this will allow us to perform single-shot decision-making on some parameters, simple channels that happened on the oscillator. And then the idea is kind of simple to the first talk we heard this morning. Instead of reconstructing the polynomial on the classical computer, what we do is that we use the qubit to implement a polynomial on the oscillator channel. Now, qubit measurement results naturally give us 0 or 1 or decision problems to that filter that we care about. And the nice thing here is that you only need one single shot. And so I think I will wrap up here due to time limit, but if you're interested, you can go ahead and look this paper. And so I wanted to highlight some open questions here. So just as we think about how the development on qubit quantum computers has advanced in the past few decades, right? If on a physical level you have an oscillator and qubit, how what can you do? So it opens a lot of new questions on different domains and fields even. So algorithms, controls, quantum error corrections, and computer architectures, or even benchmarking applications. And we wanted to seek ultimately for utility and maybe remove gates in the future again, although I introduced the gates in my talk. And with that, I will conclude here, and thank you for your attention.
We have time for one question, one quick question. If there's. Just a quick question. So the universal control, is the beam splitter necessary or not in the echo conditional displacement gate?
So if you wanted to have multiple oscillator universal control, you would need some entangling gate between different parts. So you could have beam splitter to entangle oscillators. Or if you have some qubit entangling gate, that's also fine. So the key thing is that you kind of need some entangling gate there.
Okay, thanks. All right, next is launch. So let's thanks speaker again and.